the violent birth of a solar system and a world called Earth. The story of our world begins not in tranquil isolation, but in the chaotic, violent crucible of a nascent solar system. Approximately 4.6 billion years ago, within the swirling Orion arm of the Milky Way galaxy, a dense cloud of gas and dust collapsed under its own gravity, giving birth to our Sun. This newborn star was not alone. It was surrounded by a vast, spinning disk of superheated material known as a protoplanetary disk. Within this turbulent, cloud-like environment, the fundamental building blocks of planets began to coalesce. Minute mineral grains, dancing in the heat and energy of the young sun, started to stick together in a process known as accretion. These tiny clumps, through countless collisions, grew into larger rocky chunks, then into mountain-sized planetesimals, and eventually into the first asteroids. For decades, the prevailing scientific wisdom depicted the next stage as a slow, brutal game of cosmic bumper cars, where these asteroids and planetesimals collided and gradually merged into protoplanets and finally, the planets we know today. However, a significant problem emerged with this theory. Advanced computer modeling in the late 20th and early 21st centuries began to suggest that the high-speed collisions in the early solar system were more likely to result in catastrophic shattering and destruction than in gentle mergers and growth. The puzzle of how delicate accumulation could survive such a violent environment required a new hypothesis. A major breakthrough in our understanding came from the outer reaches of our solar system. In 2019, NASA's New Horizons probe, after its historic flyby of Pluto, encountered a peculiar object in the Kuiper Belt named Arrokoth. This distant frozen relic was not a single, solid sphere but consisted of two distinct lobes connected by a slender neck, resembling a cosmic snowman. This bizarre shape told a revolutionary story. Instead of being the product of a violent impact, Arrokoth, as form indicated, a tale of two separate objects that had gently orbited one another in a synchronized dance before slowly, almost tenderly, merging together over eons. This discovery provided compelling evidence for a different model of planetary formation known as gentle clumping or pebble accretion. This theory posits that clouds of orbiting material, bound by weak gravitational forces, gradually collapsed in on themselves over vast timescales. It was through this slow, steady process of gentle clumping that the planetesimals and protoplanets, the embryonic forms of planets, were truly forged. One of these burgeoning protoplanets, forming in the Goldilocks zone, where conditions were just right for liquid water to exist, would become our Earth. The early Earth was a hellish world, a sphere of molten rock under constant bombardment from the remaining debris of the solar system's formation. But the most defining event in our planet's infancy was yet to come. Many astronomers subscribe to the giant impact hypothesis, which suggests that around 4.5 billion years ago, a Mars-sized protoplanet, often named Theia, slammed into the young Earth. This was not a glancing blow, but a cataclysmic off-center impact of almost unimaginable force. The collision generated so much heat that it effectively liquefied Earth's surface once again, turning it into a global ocean of churning, molten magma. Theia itself was utterly obliterated, and a significant portion of both bodies was vaporized and blasted into space. However, from this apocalyptic destruction came creation. Much of the ejected material, a mixture of Earth's mantle and Theia's remains, did not escape into the void. Instead, it was captured by Earth's gravity, forming a searing donut-shaped ring of rock and vapor around our planet, a new protoplanetary disk in its own right. And within this disk, the familiar process of accretion began anew. The debris started to coalesce, clumping together into larger and larger bodies until a new spherical satellite emerged from the chaos. This was the birth of our moon. This newborn companion was a dramatic sight in the early sky, looming much larger than it does today, being perhaps 16 times closer and itself a geologically active ball of magma. The giant impact hypothesis, while a violent and dramatic origin story, remains the most widely accepted model because it elegantly explains several key observations, including the moon's relatively small iron core, the similarities in oxygen isotopes between Earth and moon rocks, and the angular momentum of the Earth-Moon system. This colossal impact set the stage for everything that was to follow, from the length of our day to the stability of our climate, making Earth the unique world it is today. The lunar enigma and the scientific quest to explain our moon. For centuries, humanity has looked up at the moon with a sense of wonder, its serene presence in the night sky inspiring myths, poetry, and scientific inquiry. But the fundamental question of its origin remained one of planetary science's greatest puzzles. How did Earth acquire such a large satellite? Before the Apollo missions brought back tangible evidence, scientists relied on theoretical models, and three dominant theories competed for acceptance. The first, proposed in 1878 by George Howard Darwin, son of the famous naturalist Charles Darwin, was the fission theory. This model suggested that the early Earth was spinning so rapidly that a large blob of molten material was flung from its surface, much like mud flying off a spinning wheel. This ejected material then coalesced in orbit to form the Moon. Proponents of this theory even pointed to the basin of the Pacific Ocean as the potential scar left behind from this primordial separation. This theory had the advantage of explaining why the Moon's density is lower than Earth's, as it would be composed of lighter mantle material, and why it is tidally locked, always showing us the same face. A second hypothesis, known as the capture theory, offered a more dramatic narrative. It proposed that the Moon formed independently elsewhere in the solar system, a rogue planetary embryo wandering too close to Earth. Our planet's stronger gravity, according to this model, captured this passing object, wresting it from its original orbit and forcing it into a permanent gravitational embrace. This would explain any potential chemical differences between the two bodies. The third and seemingly most straightforward idea was the co-formation theory. This model posited that the Moon and Earth formed simultaneously from the same cloud of dust and gas at the beginning of the solar system, with the Moon simply accumulating in orbit around the growing Earth, much like the moons of Jupiter and Saturn are thought to have formed. For a long time, without concrete data, these three theories remained in a state of equilibrium, each with its own merits and flaws, and no way to decisively prove one over the others. The dawn of the space age, and particularly the Apollo program, changed everything. When Neil Armstrong and Buzz Aldrin landed on the lunar surface on July 21, 1969, they did more than just make a giant leap for mankind. They collected 21.5 kilograms of the Moon itself. Subsequent Apollo missions brought the total to nearly 400 kilograms of lunar rocks, soil, and core samples. This treasure trove of extraterrestrial material provided the hard evidence needed to test the existing theories. The analysis of these samples yielded several critical clues. First, while lunar rocks contained minerals similar to those on Earth, they were distinctly different in their detailed composition, particularly in the depletion of what scientists call volatile elements. These are elements like nitrogen, sulfur, hydrogen, and water, which evaporate easily when heated. The Moon was revealed to be incredibly dry, its rocks baked clean of these volatiles. Second, the Moon's density was confirmed to be much lower than Earth's, consistent with it having a much smaller iron core. However, the most telling clue came from the study of oxygen isotopes. The ratios of different types of oxygen atoms, O16, O17, O18, in lunar rocks were found to be virtually identical to those on Earth. This was a bombshell discovery because oxygen isotope ratios are like a chemical fingerprint, varying significantly across different regions of the solar system. The fact that Earth and the Moon shared this fingerprint meant they formed in the same part of the solar system, at roughly the same distance from the Sun. Armed with this new data, scientists began to systematically dismantle the old theories. The fission theory, while explaining the density and tidal locking, could not account for the Moon's severe depletion of volatiles. Furthermore, computer models showed that for Earth to eject a Moon-sized chunk of material, it would have had to be spinning impossibly fast, completing a rotation in about 2 hours, and the current Earth-Moon system does not possess the necessary rotational energy to have come from such a state. The capture theory also fell short. While it could explain chemical differences, the identical oxygen isotopes strongly suggested a common origin, not a capture from a distant part of the solar system. Moreover, the orbital mechanics of capturing a large object like the Moon are incredibly difficult. A passing object would likely have been slingshot away or crashed into Earth, not neatly captured. The co-formation theory, too, failed. If the Moon and Earth formed from the same material, side by side, they should be chemically identical. But the Moon's distinct lack of iron and volatiles proved they were not. With all three classic theories effectively disproven, scientists were forced back to the drawing board, leading to the development and eventual dominance of the theory that best fit all the new evidence: the giant impact hypothesis. This model, born from the ashes of the others, incorporated the clues perfectly. The similar oxygen isotopes pointed to a common origin zone. The lack of volatiles was explained by the immense heat of the impact that boiled them away. And the low iron content was because Thea's core merged with Earth's, leaving the Moon to form primarily from the iron-poor mantle material of both bodies. The mystery of Earth's water and the emergence of a habitable world. Water is the elixir of life. It covers 70% of our planet's surface, comprises 60% of the human body, and is the essential solvent for the vast majority of biological processes. Without it, Earth would be a barren desert, and life as we know it would be impossible. But the presence of so much liquid water on our world presents a profound scientific mystery. We know that the early Earth, during and immediately after its formation, was an inferno. The energy from accretion and the colossal impact with Theia would have kept the surface molten for millions of years, far too hot for any liquid water to persist. It would have instantly boiled away into space. Yet, geological evidence from ancient crystals called zircons indicates that liquid water was present on Earth's surface as early as 4.4 billion years ago. This paradox leads to the central question: if all original water was vaporized, where did our vast oceans come from? For a long time, the most appealing and straightforward answer was that water was delivered to Earth from space after the planet had cooled sufficiently. The prime suspects were comets and asteroids, which are known to contain significant amounts of ice. This delivery theory was particularly attractive because we have evidence that the inner solar system was subjected to a heavy bombardment of such objects for hundreds of millions of years after planet formation. Comets, often described as dirty snowballs, seemed like perfect celestial water carriers. To test this hypothesis, scientists needed a way to fingerprint water. It turns out that not all water is identical. While its chemical formula is always HO, the hydrogen atom can come in different isotopes. The most common form is hydrogen with one proton, but a heavier isotope called deuterium contains one proton and one neutron. The ratio of deuterium to hydrogen, the DH ratio in water, acts as a distinctive signature, varying across the solar system depending on where and under what conditions the water formed. Earth's water has a specific DH ratio of about 1.55 parts per 10,000. In 1986, the European Giotto probe analyzed the water vapor spewing from Halley's Comet. To the surprise of many, the DH ratio of Halley's water was about twice that of Earth's. This was a major blow to the comet delivery theory. Subsequent measurements of other comets from the distant Oort cloud consistently showed DH ratios that were too high to match Earth's water. Hope was rekindled with a different class of comets, the Jupiter family comets, which originate from the closer Kuiper belt. In 2010, observations of Comet Hartley 2 revealed a DH ratio that was a near-perfect match for Earth's water. It seemed the mystery was solved. However, science thrives on verification. In 2014, the Rosetta spacecraft performed a detailed analysis of Comet 6-7 P. Churyumov-Gerasimenko, another Jupiter family comet, and found its DH ratio was, once again, 3 times higher than Earth's. This contradictory data indicated that comets as a whole were too chemically diverse to be the sole source of our water. With comets largely ruled out, scientists turned their gaze to asteroids. The asteroid belt between Mars and Jupiter contains many carbonaceous chondrites, a type of asteroid rich in water-bearing minerals. The DH ratio of water locked in these asteroids is a much closer match to Earth's. This led to a revised late Veneer hypothesis, suggesting that a final wave of asteroid impacts around 4 to 3.8 billion years ago delivered a thin layer of material to Earth's surface, including precious metals and, crucially, water. This theory gained widespread acceptance, and headlines proclaimed, "Water brought to Earth by asteroids." Yet even this elegant solution has recently faced challenges. The timing is problematic. Evidence suggests Earth's oceans existed 4.3 billion years ago, predating the late heavy bombardment. Furthermore, studies of certain precious metals on Earth suggest their isotopic signatures do imperfectly match those of known asteroids. This has led to the most recent and compelling hypothesis: Earth's water has always been here. This homegrown theory posits that the building blocks of Earth itself, the planetesimals that coalesce to form our world, contained hydrated minerals rocks that have water molecules locked within their crystalline structures. While the surface was molten, these minerals deep within the mantle would have retained their water. As the planet cooled and solidified, geological activity, particularly volcanic outgassing, began to release this trapped water. Hydrogen and oxygen, bound in minerals, were freed and combined to form water vapor, which was spewed into the atmosphere by countless volcanoes. Once the Earth's crust had cooled below the boiling point of water, this vapor condensed into clouds and fell as rain, a rain that may have lasted for millennia, slowly filling the vast basins to create the first primitive oceans. This endogenous model is now gaining traction, as it aligns with the geochemical evidence and the early appearance of water. It suggests that water, the very essence of life, was not a late addition, but an integral part of Earth's composition from the very beginning, sealed within the very rocks that formed our world and patiently waiting for the right conditions to emerge and create a habitable planet. The dawn of life and Earth's transformation into a living planet. Following the violent upheavals of its formation, Earth entered the Archean Eon, a period spanning from about 4 to 2.5 billion years ago. The world was still a hostile and alien place, with a toxic atmosphere of carbon dioxide, methane, and ammonia, and no free oxygen to breathe. The land was barren volcanic rock, and the oceans, though now present, were anoxic and rich in dissolved iron, likely giving them a greenish hue. Yet in this seemingly inhospitable environment, the most profound event in our planet's history occurred: the emergence of life. The earliest life forms were not complex creatures, but simple single-celled microorganisms known as prokaryotes. These pioneers, the ancestors of all life on Earth, lacked a nucleus and other complex organelles, but possessed the fundamental characteristics of life. They were self-sustaining, could metabolize chemicals from their environment for energy, and most importantly could replicate themselves. The transition from non-living chemistry to a living organism likely involved a molecule called RNA, ribonucleic acid. RNA is unique in that it can both store genetic information, like a blueprint, and act as an enzyme to catalyze chemical reactions, including the replication of itself. This RNA world hypothesis suggests that self-replicating RNA molecules became encapsulated in protective membranes, forming the first primitive cells. Eventually, the more stable DNA, deoxyribonucleic acid, took over the role of long-term genetic storage, while RNA became the key intermediary in translating that genetic code into proteins, the workhorses of the cell. For hundreds of millions of years, these microscopic life forms were the sole inhabitants of Earth. They thrived in extreme conditions that would be lethal to most modern organisms, feeding on chemicals released from hydrothermal vents or through a process called chemosynthesis. A monumental shift occurred with the evolution of cyanobacteria. These microbes pioneered a revolutionary new way to harness energy: photosynthesis. Using sunlight, water, and carbon dioxide, they could produce their own food, and in the process, they released a waste product that would forever alter the planet oxygen. The rise of cyanobacteria made life visible on a macroscopic scale for the first time. They formed large, slimy colonies known as microbial mats and built magnificent layered rock structures called stromatolites. These domed or columnar formations grew as the cyanobacteria migrated upward through layers of sediment trapped in their sticky mats, cementing them into stone over millennia. Ancient stromatolite reefs are some of the most common fossils from the Archean Eon, providing a tangible record of Earth's earliest ecosystems. However, a fascinating puzzle, known as the Great Oxidation Event, arises here. Geological evidence indicates that despite cyanobacteria producing oxygen for possibly a billion years, significant levels of free oxygen did not begin to accumulate in the atmosphere and oceans until about 2.4 billion years ago. So where did all the oxygen go for all that time? The answer lies in the chemistry of the early oceans. The primordial seas were rich in dissolved ferrous iron, Fe², which is highly reactive with oxygen. For eons, the oxygen produced by cyanobacteria was immediately used up in oxidizing this dissolved iron, converting it into insoluble ferric iron, Fe, or rust. This rust precipitated out of the water and settled on the seafloor, forming vast, rhythmically layered deposits known as banded iron formations, BIFs. These stunning geological formations, with their alternating red, iron-rich layers and gray, silica-rich layers, are found on every continent today, and are the primary source of the world's iron ore. It is a remarkable thought that the steel in our skyscrapers, cars, And appliances originated from a planetary-scale chemical reaction, mediated by ancient bacteria over 2 billion years ago. The creation of these BIFs acted as a global oxygen sink, preventing the gas from building up in the environment for hundreds of millions of years. This long period of oxygen suppression could not last forever. Eventually, the vast reservoirs of dissolved ferrous iron in the oceans were exhausted. With nothing left to react with, the oxygen produced by countless trillions of cyanobacteria finally began to leak into the atmosphere. This triggered the Great Oxidation Event, around 2.4 billion years ago, a true planetary revolution. For the first time, Earth's atmosphere began to accumulate free oxygen. This had two transformative consequences. First, it was a catastrophe for the ancient microbial world. For most of the life forms that had evolved in an oxygen-free world, oxygen was a deadly poison. The GO likely caused the first mass extinction in Earth's history, wiping out vast swaths of anaerobic organisms and forcing life into isolated anoxic refuges. Second, and ultimately more positively, the rising oxygen levels led to the formation of the ozone layer in the upper atmosphere. This layer acted as a protective shield, filtering out the sun's harmful ultraviolet radiation. The sky turned from a hazy reddish methane mist to a clear blue, and the oceans shifted from greenish to blue. This new, oxygen-rich, UV-protected environment paved the way for the eventual evolution of more complex, oxygen-breathing life forms, setting the stage for the next dramatic act in the history of our planet. Snowball Earth, the rise of complex cells, and the boring billion. The Great Oxidation Event did not just change the atmosphere. It plunged the entire planet into a deep freeze. The introduction of vast quantities of oxygen into the air had a devastating side effect. It scrubbed out the powerful greenhouse gases that had been keeping Earth warm. Methane, a far more potent greenhouse gas than carbon dioxide, was rapidly broken down by the new oxygenic atmosphere. At the same time, the weathering of the first large supercontinent, Kennerland, pulled significant amounts of carbon dioxide out of the air. With these planetary heating blankets removed, Earth's climate system went into a precipitous cooling spiral. This triggered the Huronian glaciation, a series of ice ages that began around 2.4 billion years ago and lasted for a staggering 300 million years. This was not a typical ice age like those in recent Earth history. This was a snowball Earth event. Glaciers advanced from the poles, their brilliant white surfaces reflecting more and more sunlight back into space, a positive feedback loop known as the ice albedo effect until the ice sheets likely reached the equator, encasing the entire planet in a thick layer of ice from pole to pole. The oceans were capped by a global layer of ice, possibly a kilometer thick, turning our world into a glittering white orb in space. The question of how life survived this global deep freeze is a testament to the tenacity of microorganisms. While the surface was a frozen wasteland, life persisted in refuges. Volcanic hotspots and hydrothermal vents on the ocean floor provided oases of heat and chemical energy, melting the ice above and creating pockets of liquid water. Microbes could also have survived in subglacial lakes, within tiny brine channels trapped in the ice itself, or in cryocyanide holes, small water-filled depressions on the glacier surface caused by dark dust absorbing solar heat. The eventual thaw, which began around 2.1 billion years ago, is attributed to volcanoes. For millions of years, while the surface was frozen, volcanic activity continued unabated, relentlessly pumping carbon dioxide and other greenhouse gases into the atmosphere. With the ice cover preventing these gases from being absorbed by weathering rocks, they built up to extremely high concentrations over millions of years until the greenhouse effect became so powerful that it overwhelmed the ice albedo effect, rapidly melting the global ice cover and returning Earth to a warmer state. In the aftermath of this icy catastrophe, a new biological revolution was quietly taking place: the rise of the eukaryotes. For 2 billion years, life on Earth had been exclusively prokaryotic simple cells without a nucleus. But sometime around 1.8 to 2 billion years ago, a momentous evolutionary leap occurred. A host archaean, according to the leading theory, engulfed a bacterium. Instead of being digested, the bacterium formed a symbiotic relationship with its host, eventually evolving into an organelle called the mitochondrion. This new partnership was revolutionary. The mitochondrion acted as a powerhouse, using oxygen to metabolize food and produce energy with incredible efficiency. This new type of cell, the eukaryotic cell, was far more complex. It contained a nucleus to house its DNA and other specialized organelles. This complexity allowed for a massive increase in cell size and, crucially, set the stage for multicellularity. The earliest known eukaryotic fossils are a group of mysterious, microscopic organisms called acritarchs, which appear in the fossil record around 1.8 billion years ago. These single-celled algae were the precursors to all complex life on Earth: plants, fungi, and animals. Following this burst of evolutionary innovation, Earth entered a period of remarkable stability known as the Boring Billion, stretching from about 1.8 to 800 million years ago. Despite its name, this era was not devoid of interest. It was a time of biological and geological equilibrium. The supercontinent Columbia, or Nuna, formed and later broke apart. Oxygen levels in the atmosphere stabilized at a level much lower than today, high enough for eukaryotes to breathe but not enough to support large, active animals. The oceans remained stratified with a thin, oxygenated surface layer and vast, deep, anoxic waters below, populated by sulfur bacteria. This environmental stasis meant that evolution seemed to slow down. No major new body plans emerged. However, key developments were still happening. The first evidence of sexual reproduction appears in a red alga called Bangiomorpha around 1 billion years ago, a critical innovation for increasing genetic diversity. And towards the end of this era, the first evidence of animals emerges in the fossil record, with sponge-like fossils such as Otavia appearing around 760 million years ago. The Boring Billion was therefore not a period of stagnation but a long, necessary incubation, a quiet prelude to the explosive diversification of life that was soon to come. The enigmatic Ediacaran and the dawning of the animal kingdom. The long stability of the Boring Billion was shattered around 720 million years ago, as Earth plunged into another extreme glacial period, the Cryogenian. Once again, shifting continents and biological activity are thought to have drawn down atmospheric CO2, triggering a runaway ice albedo effect that may have created a second snowball Earth event. For 85 million years, the planet was locked in ice, but as before, volcanic outgassing eventually restored a warmer climate. As the ice retreated for the final time around 635 million years ago, Earth entered the last period of the Proterozoic Eon, the Ediacaran. The world that emerged was now familiar in its geography, with a new supercontinent, Pannotia, gracing the southern hemisphere. But the life that inhabited its oceans was truly alien. In the deep, dark waters, the first large, complex, multicellular organisms appeared. These are known as the Ediacaran biota, and they represent one of the most mysterious and fascinating chapters in the history of life. The earliest of these strange creatures were the rangeomorphs, which flourished around 570 million years ago. Organisms like Fractophysis, Bradgacia, and the towering Charnia looked less like animals and more like fronds, feathers, or fractal ferns. They possessed a unique body construction based on a fractal pattern, where large branches were composed of smaller, identical branches and those of even smaller ones. They had no obvious mouths, guts, eyes, or any organs we would recognize. Scientists have long debated what these beings were. Were they animals, giant fungi, enormous single-celled organisms, or an entirely separate kingdom of life that ultimately went extinct? The prevailing theory is that they were sessile filter feeders, or, more likely, practiced osmotrophy, absorbing dissolved organic nutrients directly from the water through their immense surface area. Their fractal design was perfectly suited for maximizing this absorption. Later in the Ediacaran, around 560 million years ago, new forms of life appeared in shallower waters. Among them were the proarticulatans, a group best exemplified by Dickinsonia. These organisms were flat, oval-shaped, and segmented, sometimes growing over a meter in length. They lay flat on the microbial mats that coated the seafloor, and trace fossils suggest they were capable of moving, perhaps gliding along in search of food. They too lack any clear digestive system, leading to speculation that they may have absorbed nutrients from the mats themselves via a mat-based digestion. A recent breakthrough in the study of Dickinsonia came from the analysis of fossilized lipid biomarkers, which revealed the presence of cholesterol, a molecule that is a hallmark of animal life. This compelling evidence strongly suggests that at least some of the Ediacaran biota were indeed early animals. The animal affinity becomes clearer with other Ediacaran fossils. Kimberella, discovered in rocks from Australia and Russia, looked like a small, slug-like creature. Associated with its fossils are scratch marks, suggesting it had a rasping feeding organ much like the radula of a modern mollusk. Most convincingly, in 2020, the fossil of a tiny, worm-like animal called Icaria wariusha was described from South Australia. Dating to 555 million years ago, this simple bilaterian animal with a front, back, and two symmetrical sides is the oldest ancestor of almost all animals, including ourselves, that has been found. It was likely the maker of simple burrows found in Ediacaran sediments. Icaria represents the humble beginning of the bilaterian body plan, a blueprint that would, in the following Cambrian period, explode into an astonishing diversity of forms. The Ediacaran period, therefore, was not a failed experiment in life's history but a critical, transitional phase. It was a time when life was testing different body plans and ecological strategies in a world still dominated by microbes. The enigmatic Ediacaran biota, from the fractal rangeomorphs to the mobile Dickinsonia and the simple, pioneering Icaria, were the evolutionary forerunners. They set the stage for the Cambrian explosion, the relatively rapid evolutionary event that would give rise to the recognizable ancestors of all modern animal phyla, ultimately paving the way for the rich tapestry of life that has populated Earth for the last 540 million years, transforming it into the vibrant planet we call home.